And
we can give some part of our tea break to Salsa, right? So we do that.
disable, enable me to participate.
Oh, you got it. Put on this one. Which one is this one?
Not this. Here. Next, someone will discuss. Hello.
Yes, ma'am. Now?
Hello. Yeah,
Hello.
that's fine. You can try it out.
Hello. Am I audible? Am I audible to everyone?
Yes, yes, you are audible.
Should we start?
Yeah.
How about this one? Powerful one. Okay.
You can see that question.
Yes. Okay. I think we do have one question from Samrat Viswas. Samrat, I have received those questions. I'll respond to you through email only. Okay. Or maybe in the last session, I'll take those questions as well. Okay. Let us start something new today. Then I'll take the question in the end. Okay. So do we start?
Thank you, sir.
Hello, everyone. Welcome back. So in the last session, we were talking about the how can we implement Markov-Chain Monte Carlo method. And for 1D probability distribution function, we try to understand that how can we find out the best fit parameter associated to a given distribution. We are going to continue with the same discussion, but today, this is the plan for today's, just give me 1 second, today's session. So these are the things which I am planning because I am going to have 2 hours lectures. So that's why we are going to divide these topics in first half and the second half. If you remember yesterday's discussion, we were having, I pointed out that whenever you are going to define a probability distribution function, sometime if you are having PDFs like Gaussian distribution function, uniform random number, uniform random numbers, Gaussian random numbers, beta distribution function, there is a long chain of PDFs that you can have. And if you want to generate the random numbers associated to those distribution, Python do have certain inbuilt library in itself. Like there is a library called random library, in which if you use random.uniform, then you can easily generate the uniform random numbers. If you use random.normal, then you can generate the normal random numbers. But it's very much possible when you will be working on a problem that you will come across a kind of probability distribution function, which is not inbuilt in your system. Okay, or inbuilt in the Python library. So we'll try to understand, in case I'll give you a random PDF, how can you generate the corresponding random numbers? Okay, this is the first thing. So because in the whole dynamics or whole analysis that we'll be doing, that will be based on the PDFs, probability distribution function. Either you are going to write down a likelihood or a prior or a posterior. We will come across these terms in a while. All these are going to be probability distribution. So we must be knowing how can we generate those. Okay. Secondly, we if you remember when we were discussing briefly about something called maximum likelihood. So in that particular discussion, I put a question mark or raised a question that most of the time we assume that our data points are coming from the Gaussian distribution only. And I named that it's based on the something called central limit theorem that gives us the freedom. So today we will try to prove it. And when I'm saying prove it, I'm not going to give you the theoretical derivation and everything. We will just try to see whether it's going to hold computationally or not. And then I'm going to give you some exercise based on that. This is then obviously we're going to continue with our discussion on MCMC. Yesterday we were doing it for 1D. I'll briefly give the overview, then go for the 2D, and then we'll see, discuss briefly about Bayes' theorem, and we'll see whether we can do some problem with real data, at least with the Hubble data. We'll try to do it. Later, in case you are interested, you can extend the same discussion for other data sets like supernova data set. You can do for BA or on any data depending on the field of interest in which you are working. Wherever you have data, you have a model, you can implement this technique. It's not like in cosmology only. I'll be discussing one case from cosmology, but it's depending on your analysis. Even in humanities or in any subject, wherever you are interested, you have data, you have model, you can obviously implement this one. Okay. And then there is a inbuilt package again, it's EMCMC, which is very popular in the sense, in case you are doing some scientific analysis for some research paper, it's instead of doing it through traditional Metropolis Hastings algorithm, this EMCMC package is based on a new sampling method called Z sampling. So that's an advanced version or even beyond the Gibbs sampling. The way we were learning the Metropolis yesterday, similarly, that's an advanced method. I don't know whether we'll be having the time for that, but I'll just try to give you the overview of that particular package so that at least you can start learning it. I'll give you the reference paper corresponding to that so that you can read about it and more details you can acquire from there. Okay, this is the plan for today's. Let's see how well we would be able to do all this stuff. Okay, so let me just start with a method. If you remember, yesterday we were discussing about two things. I pointed out that when we do work with any data and with any data and model, then there is obviously going to be one part where we'll be talking about the Bayesian statistics, means how we are treating our probability distribution function, how they are going to behave. That's come under the preview of Bayesian statistics. Once you have a probability distribution function, any sort of, it could be by the multiplication of two different probability distribution function, can be multiplication with joint probability distribution function, multiply with prior, any sort of. But Markov chain Monte Carlo in itself just a method of sampling that distribution. If you remember, yesterday we were having a 1D PDF and we were trying to sample it. So MCMC is nothing but it's the way of sampling it. If you remember yesterday's discussion, when we were discussing Monte Carlo means throwing the random numbers, Markov chain Monte Carlo was throwing the random numbers, knowing the previous position, nothing else. Okay, so that's what we were doing and that's what we did in the last class. Now, eventually the discussion will come. Yesterday, before creating any random, like any distribution, we must be knowing how can we create the random numbers associated to a distribution. Okay, so sampling from a distribution, if you remember, I'll not discuss it in detail, but yesterday I have given you a brief overview that let's say you want to sample the uniform random numbers. Okay, for uniform random numbers, you have an inbuilt command. This one we were using yesterday as well, np.random.uniform. We were using this command, but along with that and using it, let's say if I created, let's say 1000 random numbers, by using plotting the histogram, we can see these random numbers are uniformly distributed. If we'll create a large number, this is going to be more uniform in case you will plot the histogram. Now, I also talked to you about the something called linear congruential generator algorithm. This algorithm is based because the random numbers that we do create or uniform random numbers that we do create by using computers, those are not the pure random numbers, those are pseudo random numbers, and those are based on this LSG algorithm. This is a recurrence relation. I'll suggest all of you, because I'll provide it to you, but read more about it. Today we don't have time to go into the details and it's very trivial to understand it. So But I want to point out this particular linear congruential algorithm, these are based on this recurrence relation. And eventually in the method, these A, C, and M. So these are the constant. X is the random number that you will be creating. So initially, if you want to start with creating random numbers in your computer, you are supposed to provide an initial seed. Initial seed, if you'll see this iterative relation for creating first number, you will be supposed to give X naught. So that's going to be initial seed. Then this formula, this recurrence relation, A, C, and M, these are the input parameters that you are supposed to provide to your system. And once you will provide these numbers and initial seed, then it's a recurrence relation X naught to X1, X1 to X2, X2 to X3. And in that way, in a iterative manner, you will keep getting more and more uniform random numbers. But again, because your analysis is based on these particular parameters, this is not purely random. It's depending on the choice of initial seed and the choice of A, C, and M. We do call them, A is known as the like multiplier, editor, and M is the modulus relation. So you can play with it. One thing that I'll suggest to all of you, if you choose, because it's a mathematical relation, if you choose the same seed, you choose the same value of A, M, and C parameter, you run the program 1,000 times. Every time you'll be getting a same set of random numbers. Okay. Now, if you are running a program, you are, let's say you are saying, I want to run multiple samples on my data, then every time and with different set of random numbers, you want a different set of collection of random numbers. What's the point of having a same chain of random numbers? So generally in the programming languages like Python, they do use something called internal time clock of the machines. Okay. So because the time of our machine that kept changing over the time, like every moment. So they use the seed to be the time. And that's why the moment you will run the first set of random numbers, the series of random number will be different. If you'll run it after 2 minutes, the chain of random numbers will be different. That's how generally Python like programming language, they do take care that they keep generating new random number series. But mostly like Fortran, those of you must have worked with Fortran. In Fortran, if you want to change the, if you want to create a new set of random numbers and you'll just run the command from the line, you will be getting the same set of random numbers. Over there, manually, you are supposed to change the seeds. Okay, so be careful whenever you start working with random numbers in any programming language, be sure that you every time you run a program, you should be getting a completely fresh set of random numbers. Okay, so that's all about, because most of the programming languages are having this inbuilt command, so there is no point or importance of discussing this algorithm in detail. So I'll be giving it to you, you play with it. This is simple program, iterative process. I have chosen these values to be something like this. Why these numbers? They do have their own importance. Read about them. If I'm creating the same set, iterative process, I'm getting this set of random numbers. If I'll just change those numbers, you can see I'll be getting something else. Okay. So that was about the LCG. We briefly discussed about it. But now what I'm going to do, now I am assuming that I have the channel to generate the uniform random numbers by using Python, but I am having a new distribution. That distribution could be anything. That could be Gaussian, that could be exponential or something. Now our aim is starting from the uniform random numbers, how can we create a set of random numbers following a given distribution? Okay. And for that particular thing, I am going to talk about one method. There are multiple ways of doing it, but I'm just going to discuss one. It's the inverse transform method. Okay. So inverse transform method allows us to create a set of random numbers corresponding to a desired probability distribution function. Okay. Given that you know how to create uniform random numbers. Am I clear on this? Let's talk about it.
No, I am not watching the
about the
function, but come and wait.
So let's say I am having a PDF, and PDF, let me choose a exponential function, exponentially decaying function. I want to, and let's say this is X and this is PX corresponding to it. Okay. So now my aim is, if I know uniform random numbers, how can I create the set of random numbers which are following this distribution? Okay. So in the inverse transform method, it is based on a simple relation. Corresponding to every PDF, you can always plot or you can always derive corresponding CDF. CDF I mean cumulative distribution function. Okay, so if I am having x over here and I'm defining it with fx, so corresponding to every px, obviously probability distribution function, you can differentiate, find out the cumulative distribution function. Do you know what do we mean by the cumulative distribution function? Anyone? So if I am having a PDF, so then fx is defined as px dx in 1D, obviously. Starting, I am assuming that this distribution function, I am assuming, let's say this is x greater than equal to 0. I am assuming for this distribution. So I'll 0 to x, I'll integrate it. Depending on the distribution, if distribution is like minus infinity to plus infinity, depending on the range, then I'll integrate it from minus infinity to x. Right now, I have just taken it to be starting from 0. So I'm taking from 0 to x. So every time, if you'll see what I'm doing, I'm integrating my probability distribution function over the x and I'll keep plotting it. So can anyone tell me if I'm considering this px to be normalized one? Normalized distribution. So can you tell me what could be the range in which this cumulative distribution function will vary? What can be the minimum value? Minimum value is 0, obviously. What can be the maximum value? 1. See, because if I'm saying it's normalized, and if I'm plotting it from 0 to infinity px dx, given, then what is the maximum value? 1, if it is normalized. So means this distribution fx, this is always going to lie between 0 to 1. Somewhere like this. This can be anything like this shape in between, what is going to be the shape of fx, that might be varying, but asymptotically as x is going to increase, it is going to be, will be approaching to the 1 only. So it's going to lie between 0 to 1. Okay. Now what I can say, corresponding to, for a given CDF, corresponding to every x, there is going to be a fx, which is going to have a value. Let's say I'll choose this x prime some number, and then corresponding to this, I am always going to have a fx over here, and the value of fx is going to be in between 0 to 1. Yes. So if this is the case, I can use this fx. Would it be fine if I place this fx equal to a 0 to 1? What I'm saying, this fx is also going to have value between 0 to 1. And if I am able to generate the uniform random numbers corresponding to a distribution, corresponding to in a range 0 to 1, so both these distribution are going to have values between 0 to 1. So what I'm doing, I'm equating this fx equal to u. Now, if I want to, my interest is to find out x. So what I can do, if this function is implicit function, which I can write down in the form of u, wouldn't it be fine? Let me call it equal to small u, because it's just a single number. It will be one random number between 0 to 1. So I'm writing it x equal to f inverse u. If I can write it in this particular form. So whenever because I can generate thousands, millions, I do have a library. Knowing I can make this particular operation, this transfer f inverse, and then I'll be getting a set of random numbers x, and that should follow the PDF. I'm making this claim. There is beautiful theorems which you can prove. You will go to, I'll give you the material to prove them. But what I want to do here, instead of giving the doing the derivation, let's try to verify it computationally, because our focus is on learning Python as well. Okay. So let me start with a very simple example for all of you. Let us choose a PDF function, something of this sort. This is a PDF function, fx1 by lambda e to the power minus x by lambda. Okay. Now try to do, just if I'll give you 1 minute, can you try to find out the CDF corresponding to it? Just convince yourself whether you will get it. If you are having copy pen, I'll just take 1 minute to verify. What was the formula? You will integrate it from 0 to x, px dx. This is the function. Okay. Just see in case because you will be integrating it. Let me also give it to you. So I am having my px is going to be 1 by lambda e to the power minus x by lambda. Now your task is to find out fx. You are going to integrate it from 0 to infinity 0 to x because I'm interested in px dx, and we are saying it's 1 minus e to the power, let me just minus x by lambda. Okay, that's what we are saying. Now, what was the, if you are convinced with this, that's a simple integration, you don't to worry. So if I'm going to place it equal to 1 by x by lambda, I'm saying let's put it equal to u, where u is a uniform random number between 0 to 1, and make this transformation. So what it will be? So x is going to be minus 1 by lambda ln 1 plus u. Am I correct? Just check. Oh, sorry, lambda will be above. Just. Yeah. So what is the, in case, what I'm claiming, in case I'm having uniform random numbers, this is just function. I'll keep putting the values of u. I will make this transformation. And if I'll create a chain of x and then plot the histogram corresponding to that, that should follow the given distribution. Okay. So this is a simple exponential function. Let's try to do this exercise over here. Let me show you. So this is the transformation we are making. What I have done, I have defined this function x equal to exponential function we are doing, x equal to minus lambda np log 1 minus u. U we are getting from np dot random dot uniform numbers. Lambda value I have chosen. Lambda can be anything, ma'am. Yes, we have chosen it to be 2.5 for a while. Now, if I'll create this set of random numbers, let us plot it. Can you see it? See it? This is the collection of 1000 random numbers which are following the exponential distribution. Okay. Same thing. Now, this is how you can create. Now, given a distribution, but here one condition is important, that your formula, the f that you are calculating, cumulative distribution function that you are calculating, that should be transferable, means that should be implicit function explicitly written function in a manner so you can write down it in the form of u. If it is not doable, then this algorithm will face some challenges. Then you have to look for some other way of doing the same thing. Now, what I'm going to give you, this is a homework kind of thing. You can go and practice. This is a, like this kind of distribution. If you have a look on this ft, all these kind of, this is a triangular function. You are supposed to use this ft, find out the corresponding CDF, and then make the transformation and see whether you would be able to generate the random numbers corresponding to it. Because this kind of distribution you will not find in the Python inbuilt library. Let's say you are working on a problem, then you need it, then you have to create the random numbers on your own. People, especially working in the electronics, they do need it a lot. Means they do have this inbuilt, but you must be knowing how to generate by using by hand or in a traditional way. Similarly, this kind of distribution, I was trying to figure out the distribution which are not available in Python. So let's say this is a Kumar-Swamy distribution. People who might be working in geophysics, they must have come across this kind of distribution. So it's also a very important distribution. Now, the same way, I'll ask you to plot this distribution, find out the CDF, write down the inverse transform method. Same thing, nothing. Once you have this formula, x equal to this particular one, put the value of u, choose a corresponding a and b, whatsoever distribution you are following, and plot it. Like this one, I have already plotted it. So this is the, is it visible? Just it's taking a bit time. Yeah. So this was the distribution, red one, and corresponding to that, we have created the random numbers. Okay. So inverse transform method is one of the method through which you can create. Now, most useful PDF that we come across is normal distribution. Okay. For normal distribution, you will face a challenge. If you will integrate Gaussian distribution, if you will integrate the Gaussian distribution, what is the Gaussian distribution? 1 by under root 2 pi sigma e to the power minus x minus mu whole square by sigma square. Yeah, we do have this distribution. Now, corresponding to that, if I will try to calculate the cumulative distribution, minus infinity, because probability, this is going to be from minus infinity to plus infinity, minus infinity to x, px dx. Now, in the case of cumulative distribution function, you cannot solve this particular integration by hand. And this is the very much when you will have an integration of the form 0 to x e to the power minus x squared dx, this particular integration goes in the form of error function. So this is a specially defined function, and manually you cannot solve it. And if you cannot write down a functional, very explicit functional form of it, obviously you cannot make a transformation where you can explicitly write down x in the form of u. So in the case of normal distribution function or Gaussian distribution, inverse transform method will not work. Then there is a very interesting algorithm. I'll suggest all of you to go and read it. The name of the algorithm is known as the Box-Muller transformation. You can note it down. Some of you might be familiar with it. Box-Muller transformation. Okay, I'll provide you material for reading it. Okay, so Box-Muller transformation allows us to create the random numbers from uniform to normal. Okay, let me see if I have done it. Okay. Yeah, so that's what I was talking about. Can we sample the Gaussian distribution random numbers by using inverse transform method? No, reason being our fx or cumulative distribution function, that will be very complicated in sense that will be having a function called error function, which we cannot convert or write down in the form of u, or u means the uniform random numbers. Okay, so that's why we rely on this transformation called Box-Muller transformation. I have provided the link. Go and read this particular document, write down your own code. I'll suggest you. But in Python, we do have already, there is a library which is having a inbuilt command random.normal, which will give you the set of random numbers. You need not to worry about, without that you will not be able to create. But for the learning how that library is working, you should go through and write down your own program. That would be interesting. Okay, fine. So by using this algorithm or by using the command line, if I'll see your np dot, just one second, np dot random dot normal, you will give the mean, give the standard deviation, create the random numbers, plot the histogram. Using the matplotlib library, you can create all the set of random numbers. Okay, fine. Are we good till this point? So this is a brief overview that there are certain distribution which are kind of available to all of you in the form of Python library. There are going to be distribution which you would not be seeing in the libraries. Then you have to create or write down your own program to create them. Try to do this exercise given over here. That would help. Now, once we know that we can create random numbers corresponding to a given distribution, now let's go to the next step. Okay, next thing that we were trying to discuss was something about what is so special about Gaussian random numbers or Gaussian distribution. So generally in the field of astronomy, astrophysics or cosmology, whenever you will see one thing very prominently, whenever you will come across a distribution, or sorry, some measurement, that data point that you are taking or assuming, the moment you will see the data point, and if you don't have any prior knowledge about the inherent distribution from which that particular data point might be coming, then we choose to consider that this data point might be coming from the Gaussian distribution only. Now, this is not a very a strong way or a robust way of doing the things, but in case you don't have the information, any information about the inherent distribution, this is the best choice. And why I'm claiming that, assuming for a given data, assuming that it is coming from a Gaussian distribution is best choice, I'll try to show it to you. Okay, and this is supported by a theorem which is known as the center limit theorem. Again, I'm not going to prove it. For that you have to drive all the statistically, you can drive it. I'll provide you the resource, but I'll try to show you it computationally. Okay, let's talk about briefly about what do we understand from the center limit theorem. Okay, so is it clear till now? Is it making sense? Okay, so let's try to talk about the second thing, which is central limit. So, okay, what does this particular theorem states that Let's say you are having a population or a sample of data, and that data, these data points, these are the data points, thousands of the data points. Let me choose it to be, let me say these are 10 to the power 6 data points in this particular sample. I'm just randomly giving this number, and these are corresponding coming from a distribution. It can be, let's say, as any distribution you assume it to be uniform, which we have exponential or triangular, or the Kumar-Swamy distribution that we have just seen. Any distribution you can assume, because you know how to create the random numbers. Now you can create those numbers given corresponding to that distribution. Now what we can do, if I'll do one thing, I'll create several samples in it. Out of this population of numbers, I am creating these samples. Sample means I'll randomly, I'm choosing 40 points, 100 points. I'll make such samples of, let's say, 100 points. How many such samples I can create if per sample I am having 100 data points? 10 to the power 4. So I can have 10 to the power 4 such samples, each having 100 data points. Yes. Given this, now if I'll try to do one thing, corresponding to each and every sample, I'll calculate the corresponding mu. I do know how to, if I am having 100 points, I can find out their mean. Yes, that's simple. So I am calling it mu1, mu2, mu3, mu4, mu5. I can calculate this. So how many mu's I'll be having? 10 to the power 4. This is I. Am I okay with this? Let's get back to this complete population. Obviously, if it is a distribution, it will be having a mean M total, let me call it. For the total sample, it will be having a sigma as well. Let me call it sigma total. Obviously, 10 to the power 6 point, you will add them, divide by number, you will find out that their global mean. Now, I am having global mean, which is I am defining with the mu total, and global error in the sigma total that I am calculating. You can simply do it in the way you do. But if I'll make this sample, I have made 10 to the power 4 samples. Now, if I'll plot the distribution or histogram of these means, if I'll plot the histogram of these means, central limit theorem states that it is always going to be a Gaussian distribution, independent of the inherent distribution from which you have created the samples. I'm going to repeat myself. You have created 10 to the power 6 data points coming from a distribution, any distribution. Okay. Calculated corresponding mean, corresponding variance, mu total, sigma total. Now, next exercise, you have chosen the small samples, 100 points, created those samples corresponding to each small sample. You calculated their mean. So then the distribution of these means, if I am plotting, this is going to be all the mu i's. No, okay, we can talk about it. I'll just come back to that, ma'am. Yes. So there is a small size, particular limit to size. Below it should not be, but above it can be. One is 80, one is 120. That would not matter. One can try to do that. Okay. So now I am claiming this. Right now, there is a mathematical derivation to prove it, for which you have to do it from the statistical way. But right now I am stating it. Now this is going to be, this is the first thing. Second thing, the mean of these means. I am saying mean of means, because this is the distribution of all means. And if I'll calculate the mean of that, so that is going to be mu. I'm calling it C, mean corresponding to central limit theorem, is going to be equal to mu total. Mu C, the mean of the means, is going to be the mean of the global sample, and sigma of the C, because this is a Gaussian distribution, it will be having a variance. Correspondingly, you can find out this is going to be sigma total divided by under root n. So this n is the number of what is the size n over here. Okay. So now this is a claim. Right now I'm not proving it, but what we can do, we can write down a program, we can try to do this exercise, and then we can see, try to convince ourselves whether it will work or not. Yes, please. Yeah. That particular sample. Every sample, obviously, when you will be taking a sample corresponding to that, there is going to be some mean and variance as well, obviously. Yeah. Yes. No, see, can you try, if I'm understanding it correct, you are saying for this one, I'm calculating the, are you talking about this total error is, why is it going under root n? Or whole sample. So whole sample, see, whole sample, how will you calculate the error, sigma total, what, how you will calculate it? You will just try to find out x, we try to calculate this now, x square minus, or expectation value you will, or mean value will calculate. This is going to, sigma is going to be, sigma total is going to be, you will calculate the mean of the all root mean square errors, sorry, root mean square of these numbers minus the mean, square them and use this formula to calculate. This way you will be calculating the error for any distribution you calculate. So here, this sigma total is the standard deviation that you are calculating from data. Over here, this is the variance of a Gaussian distribution, because I'm claiming it to be Gaussian, that the distribution of all these are going to be Gaussian. So obviously, every sample is going to have its own error, and that's also going to have associated. So right now, I'm not associating the error of each sample with the either with the error of the total distribution, but every sample will be having the characteristic behavior of the total population in that sense. Okay. But still, isn't it like you might be having some doubts in the, isn't it beautiful? What I'm saying, whatsoever distribution, every sample in itself is having the property of the inherent distribution. But if I'll calculate the mean and plot those means, they are eventually corresponding to the Gaussian. Okay. We will prove it, then we'll try to understand why is it feasible for us to use it in the field of cosmology, astrophysics, or wherever you will come across any data. How is it, what kind of assumption we do make. Okay. So let's try to go on the program. So what I have done, okay. Yes, please. Yes, please. Yeah. Okay, right now, because these are random numbers, either you can choose them randomly, 100 coming from the, or because if I'm believing this is a pure set of random numbers, I can, in order, if I'll make that choice 100, then next 100, next 100, that will not make any change. Or you, it's up to you. If you want to just, in my case, I have chosen them 100, first 100, second 100, like in that world. Otherwise, you can choose them like randomly as well. We will see this, means after showing this, then I'll come back to that. Okay. Yes, please. See, 10 to the power 4 is not a standard number. Even creating 10 to the power 6 is not. My whole idea was just to give a sense of number. You can create as many numbers, you can create as many number of samples. Okay. Yes.
Whether we are considering the whole set, we have to take the small samples. Or can we have just half of the set and can take them?
You can do that. You can do that. It will be Gaussian. And if I'm, if though it might be seeing, even if you are going to have certain samples which are kind of overlapping, let's say this is a sample, even then it's going to work. It will not impact. You can try to do that. Okay.
Samples are non-mutually exclusive.
See, every random point that I'm saying, that is because every data point that we are taking, that's completely random. So obviously, at one point is completely independent, exclusively independent from other. If they are going to be dependent on each other, then how would we call them the random numbers? Okay. Yes, please. Yes, there is a threshold for the sample size. The threshold is on number roughly around 40. So generally, the theorem states that the number should be this number of n. It should be greater than n or greater than 40. So in case you will not be, you will be having a sample size which is smaller than 40 or so, then it will be approaching to the Gaussian. If you want to clearly see the Gaussian, then it should be quite large. Okay. So number that is, if you might be remembering, when we do these basic theorems, like when we prove that binomial theorem or Poisson, they n tends to certain large number, they approaches to the Gaussian. So that number limit is also roughly around 40. Okay, so from the simple statistical calculation, one can prove it. Okay.
So for all sample sizes, I will not see clearly the number.
But it will be leading to the Gaussian. For certain distribution like uniform, I'll show even for 10 size of 10 sample, it will prove. But in generally, to be on the safer side, we will be taking a large size for the sample data. Okay. Let's get back to the. Now, only thing, either if I want to convince you on this, either I'll prove it mathematically or I'll show it to you computationally. I'll prefer to show it computationally to all of you. So the theorem is again the same. Whatsoever the distribution, if you'll see, whatsoever the distribution, you will calculate the mean or corresponding to that. The distribution of mean of means is always going to be Gaussian, and the mean of this mean of means is going to be the independent mean of this distribution. Okay. Let's try to. I have written this, so I'll share it with all of you. Okay. Let me run this piece of code. So over here, I have created a set of uniform random numbers. I'm just first example I'm taking where I have created a set of uniform random numbers only. Okay. So I'm playing with uniform random numbers only. Now, what I did, I made, if you just see the basic for loops I'm using, I'm nothing. This is a nested for loop. Then I am having this limit of n equal to 40. N equal to 40 means I am having 1000 random numbers, uniform random numbers. Out of those 40 I have chosen. Okay, those are the size of sample I have taken. Then I have calculated the mean of sample and the extended the distribution. If I'll calculate the mean of population, so this is the number generally. If I'm having a uniform random numbers between 0 to 1, what mean would you expect? 0.5. Yeah. So because this is set, this is only 1000 points. So that's why your mean is roughly around 0.499. You can assume it to be 0.5 given some error. Then what I'm doing, I'm plotting the mean of means as well. Let me show it to you. When I was plotting the distribution, this is my distribution. I'll created 40 sample, calculated their mean, plotted that mean. That is something like this. Okay. Right now, I am just playing. How many data points are I'm having? If I am having 1000 data points and out making sample of 40, how much I will make? I'll be having 20-30 data points. With 20-30 data points, you are getting this kind of histogram. If I'll make this to be very, very large, if I'll try to make it very, very large, you will be getting, okay, it's a bit slow, it's lagging a bit. So you will be getting a distribution, something of this sort. And the mean, if you'll calculate, it will be something like 0.50. This is the mean of means for uniform distribution. Okay. Am I making sense? Are we good till this point? Now, the exercise for all of you is the following. In the previous discussion, I have given you a lot of different distribution through which you can calculate the random numbers. Exponential I have shown you, that triangular function I have shown you, I have shown you that Kumar-Swamy distribution. So you know how to create the random numbers. Okay. Now each random numbers, take the sample, find out their mean, plot it, and see whether you are able to convince yourself with the center limit theorem or not. Okay. So triangular distribution I can show. Program is very easy. You can just see. First piece of the code is creating the random numbers and then sampling it by using the sample of, I'm choosing n equal to 8 just to prove you that for n equal to 8, it will not work properly. If you'll see, mean of the population I am getting, the complete population is 0.99902 and mean of the means I'm getting like this. Okay. Standard deviation of the population is 0.41. Standard deviation of the mean of the population is 0.14. So you can see 0.41 divided by square root of 8. You will get a number similar to this because number of per sample I have chosen to be 8. So if I'll do it for a sample size of 8 numbers, plot would not be that good. but you'll increase the sample size, make it 20, then play with 40, then 100, try to see how it will go. So depending on the sample size, it will keep playing or keep showing you something else. So if I'll just show you the output, these are the random numbers which are belonging to triangular distribution function. Okay, you created those numbers. Now I have chosen the samples 8 points, and I'm plotting their distribution. I'm getting something like this. Isn't it amazing? It's like completely, when I was doing this, when I was learning a few years back, I was quite quite fascinated about it. Okay, how is it happening? We can prove it mathematically as well. I'll provide you the derivation, but for that you must be knowing a little bit about the statistics. Okay, fine. This is the task. Again, I'm going to leave you for with the distribution. This is, again, you can see I'm getting the mean, something of that sort. Now your task is to convince yourself, choose any distribution and prove it. Obviously, like chemistry, it do come up with certain exceptions as well, where it will not work. Are you familiar with Cauchy distributions? Have you heard about something called Cauchy distribution? Yeah. Or this is another Lorentz distribution, especially in spatial theory, in the solid state physics, we come across this distribution, Lorentz distribution. That's also one special case of Cauchy distribution. For that kind of distribution, it will not work. So even for Cauchy distribution, you have an inbuilt library in Python. Try to create the random numbers for Cauchy distribution using that, and then do the same task and try to convince yourself. Second, this is the first thing. Secondly, this is a question which I'm leaving for all of you. Why is it working for majority of distribution? What is so special? What is so special about the Cauchy distribution or Lorentz distribution that central limit theorem will not work for that particular distribution? What could be the case? In case I want you to do some research. In case you will come up with the answer, I am here till tomorrow, then we can discuss about that. Okay, but I'm leaving all of you so that you also get some brainstorming to do. Okay, are we good on this? So now we have achieved two tasks from today's plan. One was the sampling methods, second about central limit theorem. What I'm saying now, just try to understand the importance of this. Let's say I'm having 10 data points, the way we were started. Let's say we are considering a data, Hubble data, okay? Corresponding to one Z1 or one redshift, you are having measurement of Hubble parameter, corresponding error. Whenever you do any sort of analysis, you assume that this single data point, this is coming from a Gaussian distribution. You are able to assume it because what you are saying, you are assuming this in broad picture. Maybe this measurement might be coming from any inherent distribution. We don't know, because we cannot repeat our experiment again and again. We cannot create a sample and plot that and see the distribution. For a given redshift, we have only one single observation. Maybe this might be coming from any unknown distribution. But if I'll be having a collection of all these, collection of measurement, if I have the freedom of taking the measurement, like if it is a universe is a kitchen for me, I can make my recipe again and again and keep getting the taste, what answer I am getting. If I'll do that exercise, create the population, create the sample out of it and plot it, the mean of that is going to be Gaussian. Using central limit theorem, I can show that. So I don't know, because I am having only one single observation given one supernova event happening at one redshift, one Hubble measurement I am making, one measurement corresponding to a galaxy placed happening something in that galaxy. I am having one single measurement corresponding to that. I cannot create sample given a redshift. Then it's safe for me, instead of choosing any other associated distribution, I'll choose it to be Gaussian, believing that my central limit theorem is suggesting me to do so. Okay. But whenever we'll do that, we must be knowing and we should quote it properly in our result and in our work that we are making this assumption. Okay. You will find a lot of work where people start studying about the non-homogeneity effect in their analysis. That's obviously because on the first hand, they are assuming certain sort of homogeneous distribution. You are assuming that your observation you are making it for a Gaussian distribution when itself is kind of very symmetric. Any non-symmetric distribution will give a different distribution, a different answer. Okay. So to do any sort of Bayesian analysis, at least probability distribution function you must be knowing. And that's why it's very favorite of all the statisticians or the astronomers or cosmologists to choose their distribution to be Gaussian to begin with. Okay. Yes. Any question on this, please? Yeah.
For Gaussian distribution, the mean and variance are not defined. So would that be the reason?
That would be reason. And secondly, you will see when you will define the Cauchy distribution, there is going to be limits from 0 to x. The distribution is not going to be asymptotic in certain manner. Okay. So you have to just do a little bit digging about the Cauchy distribution. There is some very beautiful properties about it, which is different from all other distributions, including one you are pointing out, but more than that as well. Okay. Try to do that. So I am having certain questions. Let me see. Okay, one question is from Samrat. Samrat, I'll answer these questions by the end. Okay. Yeah. So first question is about observed minus expected square divide. Yes, that was an error in my analysis. Like we should write down it to be square. Even in the numerator, when you write down the chi-square, in the numerator, that's the sigma square. Maybe in my slide, that was sigma only. That was a mistake. Second one, we find out the expression of a and b by taking partial derivative of chi-square. Yes. Yesterday, if you'll see, we were doing del chi-square by del a, del chi-square by del b and finding out the expression. But how do we find the expression for sigma a and sigma b? Okay. The calculation of these particular thing, today, if you remember in the morning, I shared two books. One book by the Bevington. So you can, I cannot share the copies, e-copies online, but yeah, you can, if you'll just go on some websites, I should not talk about it. That's a copyright infringement. But there are multiple websites like PDF Drive, LibGen. Over there, you can find the e-copies of these. But I have just given you the link over there. So there's a very good book by Bevington. This is the data reduction, data analysis for the physical sciences. And then especially for astrophysics, there is a very good big book on the data reduction useful for physical sciences and the astronomical data by Phil Gregory. I have given the name of both the books. If you'll go, especially in the Bevington book, you can find out the derivation for simple chi-square. How can you find out the error on the parameters, sigma A and sigma B? There are some beautiful articles. I might share those as well, maybe by tomorrow. Samrat, I hope it's fine, and for all of you as well, in case those two like really good books, you can go and refer them. Okay. Gregory books is based on the Bayesian analysis as well. Properly, it will talk in detail because today I'll be having only 1 hour to discuss about the whole Bayes sum and everything. But that book will talk about all the priors, how to use the posterior, different cases, correlated errors. Very beautifully do discuss about all those things. Okay. I'll suggest all of you, if you are interested, go and refer that book. Okay. So this is the first half. I think, ma'am, in case we can take a break and then we'll come back and start with our MCMC part.
So we take a short tea break and do that. Yeah,
Yes.
at 12.
Right. Should I pause it?